Good morning, good evening, good afternoon, everyone. Welcome in Salesforce Apex Hour. My name is Amit, and today we are going to talk about making sense of AI model. And we have a Peter Chitam with us. Let me hand over him for his introduction and the presentation. Over to you.
Fantastic. Thanks so much, Amit. Thanks for asking me to come and speak. I think you've been trying to me to get on the show for like maybe a year now or more. And I've just been hard to pin down and, really pleased to have something to share, which is this talk called Making Sense of AI Models. I call it a tour of machine learning model architectures for non-machine learning practitioners. A little bit about myself. I worked at Salesforce for 12 years, and before that, for about 12 years, worked in enterprise software, mostly training developers and other folks on using uh, enterprise software tools, whether that was writing code for them, configuring them, even some like functional training type of stuff to help like functional consultants. My time at Salesforce, I initially was in the what we then called training and certification, which the modern day version of that is called Trailhead Academy. Worked then in developer relations as a developer evangelist, and then went on to lead the developer evangelist, and then we called them developer advocate team. And I did that up until 2023. Since then, I've left and essentially been continuing the developer relations leadership work I was doing before, and I'm advising a number of companies on how to go out and reach technical people with their content, about their products. So I call myself a developer relations advisor, and I've got a small UK based company here called Westview One. There's some links in there of my socials. So probably the one I'm most active on, particularly about Salesforce and technology, is on LinkedIn. Uh, Mostly I just sort of watch the show on Twitter these days when I'm on there. But I am also on Blue Sky and sporadic, I would say. If you want to be exposed to more personal opinions, you could watch the Blue Sky thing. I do a bit of tech posting, but also some personal stuff. And I'm using the Mataroa sort of minimalist blogging site right now for my blog. I'll probably move that to the peachittum.com domain. Actually, my Blue Sky handle on there is wrong. Should I do like a quick like edit? Boom. Okay, it's like I just changed this recently where I registered. I have peachittum.com as a domain. So boom. All right. There we go. Instant fix to my Blue Sky profile. I am at peachittum.com actually on Blue Sky. Anyway, so I do plan to add the peachittum.com to the Matarua blogging site. And if you just want to see like a lot of different presentations I've done over the years, 12 years I did developer relations and working at Salesforce. So there's quite a lot on there if you want to check it out. Take a look. And the one thing I do, oh, actually, I should mention, I am not an AI expert. My story with this is I got pretty fascinated in 2023 when everything was blowing up around generative AI, and where a lot of people went to try and learn how to write a prompt. I really was fascinated on a fundamental question, which is what exactly is an AI model? So I've been trying to backfill the knowledge and kind of learn the core ML technology and get an understanding of that. And I think in some ways, I think it's really valuable to understand what we're actually doing with this stuff. So that's where this talk came from, was to give technical practitioners in other technologies a sort of grounding in machine learning without having to do all the math, basically. So there we go. So that's kind of my thing. So the one other thing I do regularly these days is Paul Battison and I have a live stream, live coding session that we do every 2 weeks for 2 hours on a Thursday. If you're US based, it's a little early for you. We do it about 1 p.m. UK time. But pop on and take a look if you're interested, or catch the on demand. We always record them and they're on there on the YouTube channel as well. Right now, we've been actually building a Salesforce CLI plugin, and starting this coming week, we have kind of an idea for a larger plugin, like to just kind of build a more cohesive plugin out of that. So it's been fun keeping my hands dirty and working with the technology with Salesforce, now that I don't work for Salesforce anymore. All right. So the agenda here today, I'm gonna hopefully answer that question: what is an AI model? I then want to talk about, kind of walk through how you train and then use a model using a very simple machine learning algorithm called linear regression. From there, we'll do kind of an overview of common, what we would now call predictive AI models. Then jump into generative AI, and then I just have a short kind of bit about agents to. It's really more food for thought than to say anything definitive. I think at some point in time I could see doing a full version of this that was just like 30 minutes on breaking down agents, different kinds of agents, and that sort of thing. That's a really fascinating discussion, because agent can mean so many things in the context of AI agents. But just going to be scratching the surface on that. All right. Uh, and like I said, this was the inspiring question for this talk. Um, what is a model? And I think I was annoyed that it was a term that was used so often as people were describing what they were doing with generative AI, and how they were trying to solve a particular problem. And then you would hear, and I use such and such a model which had this many parameters and this many tokens, and I just wanted to know what that meant exactly. And that's kind of that tends to be a motivating thing for me. Is I don't do well with terms that are sort of abstract, or terms that are overloaded. Model can mean like lots of things, and when you're talking about something like generative AI, what exactly does that mean? So I really wanted to be able to verbalize what exactly a model is, and again, in a way that I didn't want to, I, I I felt like there had to be a way to describe this without actually knowing the fundamental linear algebra and calculus and statistics that sit behind all these models. So, what is a model? Basically, every AI model has these things in common, in that there's going to be a set of inputs, and generally, these inputs tend to be referred to as features. Uh, there's going to be an algorithm that is the kind of the engine of how that model thinks or performs its calculations. There's going to be a set of learned data, and this is where that term parameters comes from. And parameters are the way that you sort of take an input feature, run it through the algorithm, and then get a useful prediction. And that's the fourth aspect of a model, is that there's some prediction that's made. Prediction is, another way to think about that is the output of inference being the process of a model making a prediction. So there we go. So I think, to me, this is the best general purpose description of a model that I've been able to up with, and frankly, that I've heard from everyone else. And so with that, I'd like to thank you for my presentation. And yeah, I'm just kidding. There's a lot more to say besides that. So let's talk about inference again, because if we break down what exactly the model is, there's, like we said, there's an algorithm and there's some learned data that we call parameters. And then there's that input data. Again, we call that features. And oftentimes in machine learning, there's going to be a lot of different features for a model. And then we have that output data, which is the prediction. But the really key thing is answering that question: what exactly is this learned data, and how does it learn? Well, that's the training process. And the training process essentially mimics inference. But the difference is you're going to have your features, right? So these are the data that you're going to input into the algorithm. And you're going to also have some parameters that are, you know, essentially unknown, right? And we call this initializing your parameters. And when you initialize parameters, you either initialize them to zeros, or you maybe randomly initialize them, or you might use the feature data to initialize them. Right. So any of these things are potentially the way to initialize the parameters. But the fundamental thing to understand is that, at the beginning, at the outset of model training, the parameters are not useful. So your output is pretty much rubbish to begin with. Or rather, it's not useful. And so what you do is you take the output and then you do something that's called a cost function. And essentially what you're doing is you're measuring, how good that output was against what would be a hoped for or expected output. And the expected outputs when you have it are also sometimes called targets, right? So if your training data has some known outputs that you're training with, those will be called targets. The cost function comes up with a value, and then using that information, we're going to tweak the parameters a little bit. And this process in certain algorithms can be called gradient descent. This is where the calculus comes in, where we kind of nudge the parameters in a direction, based on some calculus that say, let's modify these and see if we made them better. And then we repeat this process, hundreds, thousands, millions of times. And then at some point in time, the model basically becomes useful. So let's walk through a specific use case with this using linear regression. We're going to use a use case that is kind of a classic example use case that happens with, or that comes along with learning machine learning, which is house price data. I think this is a really widely available open data set. It changes all the time, so it can kind of remain interesting. And it has a fairly good set of features that you can make predictions with, things like the area of your house, either in square feet or square meters, number of rooms, what postcode it's in, things about other aspects of the neighborhood, like are there freeways or motorways nearby? Are there schools, shopping? So all of those things could be potentially features that could impact what the house price is. And so with our training data, we're going to take all of the features and the known house price for past sales and use that to train our model. So linear regression, if you've done any training in statistics, this is the same linear regression that you would have studied in your statistics class. It is still a machine learning algorithm because you can basically automate it using the linear regression algorithm, and there are a number of really useful libraries that package this up really nice and neatly, so you don't need to ever write the linear regression algorithm. It's in a package somewhere in a JavaScript library or Python library, and you're good to go. It's a very good basic statistical prediction tool, especially if you want to predict a sort of, virtually infinite numeric, possible numeric output. And that's really where linear regression comes in. So we have our model, we predict some number. And we're going to take that house data that I talked about, but instead of using all of those features, in order to illustrate how learning works in linear regression, we're going to simplify this down to just a single feature. And that feature is area in square meters, right? So actually, it could be square feet. I think I forget. I think the sample data I did later probably was square feet. I've given this talk for both American audiences and European audiences, and I think it's a bit mishmashed right now. But we'll just stick with area for now. So we have our area, we have our house price. The area is our feature. The house price is our target, right? What we want to train for the output, train the model to output eventually. And we're going to plot those on a simple graph where the x-axis is the area, the y-axis is the price. We plot out all of our data points, and we essentially then look to see, what is the kind of midpoint of all of those data points. right? And that midpoint line is going to give us a couple of measurements. One of those measurements is called the bias, and that would essentially be what's the value on that y-axis where the line crosses the y-axis. And the other one is the slope of the line, and that's referred to as the weight. And what you can see in this illustration is if you have the bias and the weight, you can understand for the area of your house what the correlation is to the price of that house. But again, we need to think about this in a more complex set of features. This is just a two-dimensional graph with one single feature. If you then add another feature, then it's three-dimensional, and yet another feature, then it's four-dimensional, and then we stop being able to visualize or really reason about it with our brains. And so this is where kind of the learning algorithm comes in. So again, to simplify back to this one feature, essentially, when we go through training, remember the goal is to minimize the cost function. We're trying to get the lowest difference between where our line is drawn and all of the data points that we have. So we initialize our features, our bias and our weight, and we could end up with a line that looked like this perhaps, if we initialize it that way. We could have also initialized everything to 0 and it would have just been flat across the bottom. How you initialize it kind of depends on your approach to a particular model. Once we get that initial plotted, line for this graph, we're then going to measure all of the differences between where the line is and where the plotted points are. We're going to average those and come up with a measurement that is our error or a cost of this particular set of features. We'll then adjust our guess and try again. And so this is the process of learning where, you make the prediction with the new set of feature values, you you do the cost function, you come up with your cost value, and then you go through gradient descent, you make some adjustment to those values, and then you repeat that process and you go through that over and over. Now, I am greatly simplifying this, of course. So anybody who has some machine learning background will know that like it's not just as simple as making some changes, and there are places where you can kind of get caught in the process of doing this. Um, and there are different algorithms to use to actually, to make those changes to the weight and the bias. So there's a lot more to it, but like I said, this is a simplification so you can kind of understand how this works without really getting into the nitty gritty of all the math. So once we get to the point where, usually what's going to happen is our cost function between training runs is going to stop changing that much, right? And once we get to that point where it's not really changing anymore, we can say that the model has converged. In other words, we know that for feature X, um, we have the best weight and bias values to determine the best price for a particular area of a house, right? That would be model convergence. And then we're good to go. We can now do inference. So we can then say if some new house comes in and that house is 3,500 square feet, for example, we might know that the cost of the house is going to be $850,000, for instance, right? And that is basically how training happens, and we move into inference. Now, of course, different algorithms have different steps and processes and uh, uh, different mathematical algorithms that they use behind it. But this fundamental process of starting with a baseline, making a guess, making a change to your baseline, and then making another guess and measuring it each step along the way until you get to a point where your guesses aren't really improving anymore. That is essentially how training works for many machine learning algorithms. Now, just to revisit this, like I said, we just used area for this example, but the reality is you're going to have many more features in any given robust machine learning algorithm. And so for that reason, when we talk about introducing how machine learning training and inference works, it's a lot easier to just pick the one feature. But the reality is you're going to have a lot more features than that um, in your training process. But the important thing to realize is that the learning algorithm doesn't really change. Yes, it's more complex. You are doing with matrix multiplication as opposed to just simple multiplication of like a single number. Um, but again, there are really excellent libraries that make this super easy to actually do in code. It can be less than 50 lines of code to go through and train, a simple, uh, even a simple neural network model. It doesn't take a lot of code to do that if you're using something like PyTorch or TensorFlow. And of course, it's worth saying that there is no finish line in machine learning. Your model is never really done. There's always new data that comes in. There is old data that ages out, and there are things like data drift, where certain features may be proportionally less relevant, and if you don't make adjustments to your model, that may throw off the model's results. Some features may just become less relevant entirely because of either seasonal changes or changes in sort of cultural behavior of the humans that you're trying to predict about. So any of those things can cause your data to shift over time. And so, as a best practice, you aren't just training the model once and then using it forever. You are constantly updating the model with new information. Now, one thing that's good to do here, since this is a Salesforce audience, this is a great point to do some contextualization of what you see in your Salesforce org when you go to Model Builder. Now, Model Builder has ways that you can do predictive AI models instead of generative AI models. And one of them is called the general linear model. This is actually linear regression in your org. So even easier than picking up PyTorch or TensorFlow and creating a machine learning model that uses linear regression, you can just simply go into Model Builder and use a general linear model and do linear regression on your Salesforce data today. Linear regression still is a good algorithm for doing basic numeric scoring. You can also do classification with linear regression. So based on the range of the value, you can certainly assign classifications to that. And it is a simple and fast model to implement. So it's just something to bear in mind that there may be cases where you might think, oh, I'm going to go use an LLM for this. This may be faster and possibly cheaper. Although these days, with what's just happened with DeepSeek, this is all getting thrown up in the air as far as how expensive inference is going to cost in the next few months. But I think there are still overhead, and there's still overhead and implementation costs to getting a generative AI model to work that may be less than getting something like this general linear model to work. All right. Um, So this is actually a good time to just check in with folks and see any questions about that. Like, did anything kind of like not quite make sense, or is there anything that you'd like to sort of pop into the questions? And I am looking at the chat. I don't see anything. Um, Anyway, that's fine. We'll come back in the end. We should have some time for Q&A at the end. So if anything that I just said about linear regression or basic training and inference of AI models, if anything's kind of, knocking around in your head and you'd like to kind of put that out there, I'd love to see it in the chat. One of the reasons I wanted to do this live was hopefully get some interaction with folks and get people talking or chatting on the text chat. So cool. All right, so this next section is really kind of a harbor tour of other predictive AI algorithms, just to give you a sense for some of the other things that are out there. And I like coming back to this idea that basically modern machine learning based AI is about finding connections through math, or maths if you're based in the UK. Um, and to me, it is a bit magical how well some of these algorithms can do their jobs. There's some broad categories of machine learning. So supervised learning, unsupervised learning, and reinforcement learning. When we're talking about predictive AI models, sort of leaving generative AI out of this for the moment. Supervised learning is where your training data has all the inputs, the features, and a known output, also known as a target. And then you basically go through that training process so that it learns something, that it learns to find the correlation between those inputs and outputs. Unsupervised learning, I think, is super cool because it's essentially, here's a bunch of data, and you're going to use those machine learning models to find the patterns in your data themselves. Um, I think that those are some of my favorite algorithms. And then reinforcement learning. Um, this is kind of its own separate category. I used to get this very confused with unsupervised learning, but reinforcement learning is, essentially you have an algorithm or an agent, actually, it's often called, that is learning an environment or a problem space so that it can make predictions on how to operate independently in that environment or that problem space. Um, so yeah, so that's reinforcement learning. Uh, and what I would say is, for those of you who've been working with generative AI or following what's going on, the typical, or the sort of classical transformer based generative AI model is actually a combination of supervised and reinforcement learning in most cases. So just to kind of bear in mind, generative AI models are sort of composites of several different algorithms. All right. And this is just kind of a nice laundry list of specific algorithms and where they fall under these different categories. I'm not going to spend a lot of time on this right now. Reading a list of things is not that entertaining. So let's just jump in and see what they are. Now, classification algorithms, or sometimes called logistic regression, are very similar to linear regression, but they're very focused on finding a discrete set of values. So here, the discrete set of values could be sort of a yes, no, sort of Boolean output, or it could be multiple, so it'd be like, a set of values that, perhaps is like, 10 or 20 even. It could even be numeric, provided is a discrete set of numbers. So for instance, in our house use case that we talked about before, obviously there are not an infinite number of rooms in houses. In fact, the vast majority of houses have somewhere between probably 1 and 5. I think if you included that in your data set, you would be hitting, 99% of actual houses that exist in the world. And then more than that's going to be a very small set. But even if you went up to 25 rooms, let's say, and you were including your, stately manors here in the UK, you're still talking about a discrete set of numeric values, um, as opposed to, sort of an infinite number, or a decimal based number even. So just keep that in mind as far as the difference between logistic regression and linear regression, when it comes to number values. Now, if you take some of these more simple machine learning algorithms and you stack them together so that you input all of your features into a whole bunch of these in a layer, and those goes passed to another layer, and those outputs get passed to yet another layer. Now you have what's called a neural network. And that's essentially what you're networking, is a bunch of more simple machine learning algorithms that each do their own calculation and each learn their own information about the features that you are sending in. They have their own set of parameters, and then they output something. Um, Now, the sort of classical picture that you see drawn here would be known as a feed forward neural network, and that's basically where the algorithm moves data one direction and then outputs it. There's also something called a recurrent neural network, which I've not illustrated here, where the output gets fed back through maybe the same layer or sets of layers multiple times. And incidentally, recurrent neural networks were the classical uh, natural language processing algorithm before the modern generative AI algorithms took off a few years ago. So that's what neural networks essentially are, is a whole bunch of smaller, more simple machine learning algorithms working together. Now, decision trees get left out of a lot of machine learning overviews. They were part of the training that I took to kind of learn basic machine learning. And I think that was a really smart choice on the part of, so I took the deeplearning.ai course, their basic machine learning course. Um, they are still very good for complex classification. They also are typically much more interpretable than a neural network like this. One of the problems with neural networks is, if for instance, I wanted to try and understand like what was this node right here? Like what was it thinking? It's very difficult to understand that. And there's a huge amount of research being done on that right now so that more trust can be had of generative AI, in fact. But interpretability is a problem for neural networks, whereas decision trees, they are very transparent. Typically, when a decision is made, you sort of know why it was made because each node in the decision tree basically boils down to some characteristic that it is making the decision upon. Decision trees also tend to do really well in machine learning contests where, somebody brings up a data set and says, okay, find out this thing about this data set. You see them doing, you see oftentimes decision trees being used in those contests. And this is another good point to circle back around to Model Builder, because the other two types of models that you have available for predictive models in Model Builder are both decision trees. So the first one is called a gradient boosting machine. This is a more simple decision tree. And if your data set is on the small side, it's better for that. It's also better for interpretability. The other type is called XGBoost, better for larger data sets. And in those larger data sets, it said that they can typically generalize better. And what that means, so generalization, it refers to when you train your model, how well it performs against the data set it was trained on is measured by precision. And so if you train your model and it doesn't perform well on the data set that it was trained on, that means that it never really converged and it's not a precise model. And that's often referred to as underfitting. The opposite problem is when your model got so good at the training data set, it can perform really well with the training data set, but when you give it new data, it's sort of overlearned that training data set and it stops performing well. And that's called overfitting. Um, when something is overfitting, it's said to not generalize well. In other words, it doesn't work well outside of its original data set. It doesn't work well against a general data set. So that's one of the things that the XGBoost algorithm has going for it is better generalization for those larger data sets. And there are some algorithms that can control tree size and kind of keep things under wraps as well. So just a couple of tree model options. And these, typically when you want to do sort of more complex classification, that's where you want to use one of these. All right, so getting on to unsupervised learning, just checking my time. Yep, doing pretty good. Clustering algorithms are one form of this. These are super cool because you kind of have a bunch of data and you sort of throw it at the model, and then the model kind of figures out, okay, like this has these things in it. And the way that clustering algorithms work is that you want to tell it how many classifications it should look for. And of course, this is really dependent on the data, right? Like what's the use case that you're looking for? It's not just random. But let's say, you're looking for it to classify two things for this data set. It could go and find where the, general groupings of these things are. Likewise, you could take the exact same data set and you could say, actually find three groupings, and it might look something like this. So that's really what clustering algorithms are for. And clustering algorithms work well when you have a large data set and it is known data. Now, if you have either a small data set or you're trying to find problems that are novel, um, then you can use what's called an anomaly detection algorithm. And anomaly detection uses kind of typical Gaussian distribution, where you take your data points and you do the Gaussian distribution, and you sort of learn what your bell curve is going to look like for that, and kind of where the midpoint is that in that. And then once you have that data for your training set, what's great is that you can test new things that you didn't train on at all. And so if one event happens and it kind of falls here in as far as compared to the training set, then you could say, well, that looks pretty ordinary. It looks more normal, right? It is not an anomaly. But if something is sort of way outside of the standard deviation, then you can turn around and say, actually, this looks abnormal, and we want to investigate that or flag it or fire an alert or whatever. And as you can imagine, anomaly detections are really good for things like fraud detection or IT systems incursions and that sort of thing, because you can kind of take your past logs of your system behavior and you sort of throw it at the anomaly detection algorithm. It then comes up with the distribution. And then if things look different at any point, it will kind of pop up and it'll get flagged to the attention of the anomaly detection algorithm. So, yeah, so what we're looking for is like a new event that occurs that looks like a low probability event, essentially. And then the last uh, unsupervised learning algorithm I'll talk about is recommenders. Recommenders have been around. I used to work with a marketing software package in about 2002 that had a recommender. So recommenders are tried and true and have been around for a long, long time. And I think we're all very used to them, where we go to an e-commerce site, we're looking at a page with some product in it, and then it tells us, hey, you might want to look at all these other things, right? So you can probably guess I was looking at a website where I was looking at a bicycle tire, and that's where I found all of these recommendations on a local biking website here in the UK. And then just to talk about reinforcement learning quickly, and reinforcement learning is important in the context of generative AI because it is one of the steps that OpenAI kind of innovated to take large language models and kind of push them beyond where they had been before. When they got to GPT-3, I think is when they first innovated that. And with reinforcement learning, you essentially have an agent, and this agent has a set of policies. In other words, it has some rules that it's been told to follow. The agent takes action in an environment, and then once that action has completed, the environment is going to send the new state to the agent, or the agent's going to detect the new state, along with a reward. Now, that reward works with the policy to then kind of determine the next action to take. And when you train a reinforcement learning model, essentially you're doing this process over and over again. Now, I popped this picture of Donkey Kong up here, or this GIF of Donkey Kong. That's not a gratuitous thing. That is actually the Code Bullet YouTube channel, where he wrote a version of the Donkey Kong game, and then he used several different reinforcement learning algorithms to train a Donkey Kong agent, which is it's very funny podcast actually. And what I love how it sort of shows the learning process of this swarm of Marios, trying to kind of figure out how to get their way up the scaffolding in Donkey Kong, and it's a good analogy and good visual for how reinforcement learning works. All right, so let's move on to generative AI. This is really kind of the state of the art these days, obviously, and I use the term generative AI because it I think it's still the best way to describe these models. Even LLMs are one form of this. Generative AI also exists now for multimodal. problems related to video generation, image generation, sound generation, and you can go from like sound to text. So there's all kinds of ways that generative AI, uh, are working their way into how we do our work, in fact. And again, just to bring another quote in here, I think this is definitely true. And I still feel this over and over again as I continue to work with generative AI tools. I was just trying to do some research a couple of weeks ago, and I was using the ChatGPT 4.0 model. And I was literally kind of providing some questions and getting some data and passing it to the to 4.0, and it would actually generate the Python code. I could see the Python code, and it would generate graphs for this data. It's like I think of where what it used to take to do these sorts of things when I first started in the 1990s, and it is pretty amazing. So let's talk about these. The transformer was the invention in a paper called Attention is All You Need, and it was named that for this one particular algorithm that's called the attention mechanism. It came out in 2017 and it really surprised a lot of people. It was an innovation because previously they'd been using these recurrent neural networks. They had used attention as well, but the innovation here was basically to dump the recurrent neural network, just focus on attention and find a way to use that as the core piece of this model. Um, what it allowed for primarily was to parallelize the inputs, and that made for a much more efficient model. It allowed for larger bodies of text, which meant it scaled better. There was less data loss. There were all kinds of things that just by making this tweak and getting rid of what had been the state of the art and trying something completely new, or novel, I should say, as far as how to use this device, um, you know, produced something that was completely unexpected, and it generalized better than recurrent neural networks. The other thing that they discovered was that when they scaled it, it produced unplanned behaviors. And the word that they used for this was emergent behaviors. The original transformer was actually designed for translation. But what they discovered is if they scaled it enough, it could also do text classification, which was unexpected. And that really pushed the research in the direction of let's see what happens if we just scale this more, tweak this algorithm, tweak this architecture, and scale, scale, scale. And that's kind of led us to where we are today. So there's just to call out, this is the actual diagram from the original Transformer paper. That's where I got it from. I didn't make this up, but that's where that multi-headed attention thing is. That's the attention mechanism. Now, the actual model itself is a little bit different. Like I said, it's really a composite of a bunch of different algorithms. In fact, there's a traditional feed forward neural network in there. There's an algorithm called softmax, which is kind of a statistical ranking algorithm. So there's a whole bunch of things that go into what makes a generative AI model. And that's really all of the algorithms. You also have all the parameters. Again, these are things that we're going to learn at each step along the way, each layer within the model. There's something called there's what I refer to as a vocabulary in this slide. Um, and then there's something called embeddings, which is essentially identifying the meaning and the relationship between all the different, words, let's call them, in the vocabulary. And so with that, our model is going to receive some kind of input, and we call that a prompt, and then it produces an output, and we call that a completion. And the key thing that is the real difference that I really only gave myself 10 minutes to talk about this, so I'm not going to go super deep. But I wanted to talk a little bit about this vocabulary thing because that's what we refer to as the tokens. The number of tokens that a model is trained on essentially identifies, the words that it's going to be able to understand when it produces, when it gets input and when it produces completions. And one of the interesting things about that is words are words, right? Those of us who have worked in technology, when you're doing text processing, underneath that, words have to represent something that's mathematical and computational. And that's really where the concept of a token comes in, because those tokens, whether they're words or fragments of words or groups of words, like sentences or paragraphs, or groups of text, like in a code generation model, that could be a method in a class, for instance, or it could be a statement, right? Any of those things can potentially be a token. The model never really knows the human text version of that token. It's just going to have a token identifier, right? So there's going to be a number that in the model represents the word why or do or admins or drink. And then each one of those tokens is going to have an embeddings vector. And that embeddings vector is going to have a whole bunch of features that help identify the relationship between this token and all of the other tokens in the broader vocabulary of the model. And I think it helps to sort of visualize this in a 3D way. Yes, for sure. You know, if you think about it, you know, that embeddings vector, I think has something like 768 different features in it, right? So it's impossible for us to again visualize more than 3 dimensions. You can't visualize a 768 dimension space, right? But this tool here, which is the TensorFlow projector, is a way of taking that, many dimensional space and kind of turning it into a 3 dimensional space that we can begin to understand. And I think it's great because so I did a search on drink and I found the word drink here. You can see up there. And you can see how in this particular token body, and this comes from the word to vec token tool. You can see all the different things that relate to drink. And in fact, I can kind of zoom in on it, right? And I can see that like trip, habit, buy. I don't know why you would wear your drink, but things like drinking and eaten are in there. And then, you can kind of see how all these things relate to that word drink. So that just kind of gives you an idea. I find this useful to help visualize what exactly does a model think about text, right? Well, that's basically how models, when they have, the tokens that they have and the embeddings that they have, that's really how they understand, the tokens. So we're going to take our input and we're going to take our embeddings. In addition to the embeddings, there's going to be an encoding of the word order of our input. And there's going to be encoding that presents a sort of weighted relationship from each word to all of the other words in the model. That's the actual input because, why admins drink is never going to see the model except in a numeric representation of those tokens and the embeddings of those tokens and the order and then the relationship to each other. That's what gets fed through many layers of a transformer. And each new transformer models slightly configures or changes how those attention blocks work. And then we're going to get an output. Now the output is going to be a ranking of every single word or token in the vocabulary of that model. And that weighting is going to tell us the words that are sort of most likely to come next. And let me get my little pointer here. Right. So most likely to come next and, possibly least likely to come next, like these ones here. Right. And then we have to pick the next token because in the end, that's the job of the model. Like, what's the token you're actually going to generate? And that's where token selection comes in. Probably most people have heard the term temperature. That's a pretty well known uh, they call these hyperparameters. So the temperature hyperparameter allows, for greater or lesser degrees of variability in what the output is. Like you set the temperature to 0, and then you're going to pretty much get the same generation over and over again for an input. You set it to like 2, and you get crazy stuff coming out of your model. Um, on the other hand, you can actually turn down sampling completely by setting the token selection to greedy. So most models have an option to just say, don't do any randomization of the output, just pick the most likely token each time, which is, of course, going to be boring. And then you can also specify a top number of tokens to select from, either based on number or overall probability. So you could say pick the top, you know, pick from the top 50 most likely tokens, right? And that's a way of like maybe turning your temperature up, but reducing the variability or controlling the variability a little bit. Or you could say, set your temperature up, but then, only pick from the top 10% of tokens. And that's what the top P um, setting is for. So top K is the top N number of tokens, and top P is the top um, uh, probability of tokens to select from. And that's basically how transformers work. And this was really my goal with this, is to help people understand like what exactly is going on when a transformer takes your utterance, right, your input, and does something with it. And again, great oversimplification. If you've been like maybe even writing the algorithm, because you can actually go out there and there are YouTube channels where somebody will walk you through writing your own transformer. That's great if you're doing that. But like I said, this is really for people who are never going to be doing that. I want you to understand like how exactly this technically works. Which brings up a really interesting point, and that is model selection. And I've kind of hinted at that before. When you go through model selection, you need to understand what your use case is, because that's going to determine, first and foremost, which types of models you want to pick from. If you're doing a simple, numeric prediction, yeah, you could do that with a transformer model. That's certainly possible. Um, but is it the best way to do it? I mean, that really is a question that you can ask. It may be the easiest, but you might find that it costs a lot to do it as well. You're sort of balloon hunting with a shotgun, so to speak. Um, Once you've kind of narrowed down which types of models are good ones to pick from, then you kind of need to think about costs for producing that, for actually producing the feature you want, how much time it's going to take, and what's the skill set of your team. Like, just like any software project, it's the same equation, really. What do you want to do? How much is going to cost? How much time do you have? And what are your skills? So I want people to come back to this, because I think it's really easy right now to just sort of want to throw a large language model or generative AI at everything. And I think, even Salesforce gives us a lot of tools to potentially use beyond just another large language model. Okay. So I've got 5 minutes to wrap up here to come up on the hour. I just want to do a quick word about agents, because obviously that is everywhere right now. What makes an agent are these characteristics. And, I've seen this couched in a bunch of different ways, but, generally an agent needs to have some ability to perceive the environment that they're operating in. And along with that, oftentimes some knowledge and some memory is helpful, like some grounding as far as the data. The agent needs to be able to plan. It needs some access to tools to do something with. And this can be either physical tools in the case of a robot, or, tools as in software. And then it needs to be able to take action. And the way that that all kind of plays out, interestingly, looks a lot like reinforcement learning. The difference, though, comes in the thinking part of it. You might say, right? Especially when it comes to generative AI agents, which is kind of what a lot of us are dealing with right now. Right? So we have our agent, and we have the environment that it's going to operate in. The key thing is that agent needs to be able to perceive information about that environment, relevant information. Um, that agent then needs to be able to reason about what it has detected in the environment, and then it needs to be able to take action in the environment. Those are the key pieces of the agent. The big difference being here is that the reasoning, in the case of reinforcement learning, you basically have the reinforcement learning algorithm, and you just keep throwing the agent at the environment until it figures itself out, as far as how to operate within the confines um, of its policies, right? In the case of the agents that we're looking at, as far as Agent Force, the reasoning is going to probably be coming from a large language model, in fact. And, I think it's also important to sort of ground ourselves in this onslaught of everything agent right now. This was just a month ago where, it's being uttered that 2025 is already the year of AI agents. Um, I just want to take a moment and really ground ourselves in that agents have been around for like a long time. I don't know if anybody had a Roomba vacuum back in 2002, but by the classic definition of an agent, this is an agent. Agents can be robots. And in fact, most of the agents that are out there that are operating in the real world, a lot of them tend to be robots, or they tend to be these devices that we've all become very, very used to. Now, obviously, the landscape has changed massively. And the thing that I would say is really interesting is that, what we have now in front of us are frameworks and software packages that make it really easy for us to implement AI agents using these state of the art large language models and generative AI. I've I've popped a few examples of some of the more common frameworks that are out there. Things like LangGraph, AutoGen, Llama Index. These are actual agent frameworks that are available and probably are being used in production today. Operator is the new one from OpenAI, which I have to get onto a VPN to access it yet, and I've been too lazy to do that, so I've not really played with it. And of course, Agent Force, we all have to think back to that. Um, the key thing that I want to, end with here is that, agents are kind of being thrown at us right now as this brand new thing. And they're not. They're really not. How we use them has absolutely transformed. And the one thing that I really appreciate about Agent Force is that all of these other agent frameworks out there, you really need to be a software developer, or possibly a machine learning engineer, or an AI engineer to manage these and to use them. Agent Force, when it was first brought out in its uh, Einstein Copilot form, before anybody was saying agent, I could see that Salesforce was trying to build a agent framework in Salesforce's way. And I do think that's to be applauded. I think, it's got a lot of room to grow, is a good way to put it. But at the same time, I can see Salesforce moving the direction in the same way, and I would say also with some of the same limitations that Flow provides automation to people who don't necessarily write code. I think Agent Force is going to bring some probably pretty powerful machine learning capabilities, again, to people who don't code, don't want to code, and never will code. And I think that's the thing to end on here is, that's really the direction that we're going um, in this world. So there we go. Hopefully that gave you a really good overview and solid grounding in the mechanics of these models, how they work, how they get trained, the difference between different kinds of models, which predictive models you can use today in Salesforce, and maybe a bit more grounding and understanding on how to get a large language model or generative AI to work for you. And with that, I want to say thank you. I'm up against time, but I'm happy to stay on for a few minutes if there are any questions.
Thank you, Peter, for such a great session. Anybody have any question, feel free to unmute yourself and ask a question or put into the chat window. Feel free to
Crickets.
unmute yourself.
Hey, Peter, Don Robbins here. Can you hear me okay?
Hey, Don.
Good good morning, as well, my morning. I guess it's a little later for you. I came in late to the presentation, but I heard you mention something about some training that you had taken around AI. Do you have a list of courses that you have explored?
Yeah, and yeah, I thought about that, and I think what I can do is I can go back and post that on the LinkedIn posting for Apex Hours for this live stream. That might be the easiest way to make
Yeah,
them available to everybody.
that would be great. Thank you. See you
Yeah,
soon.
you bet. Thanks, Don.
Any other question from anyone? Nice to see you, Don. So there is a question, are all the AIs stateless?
That's a good question. So, um, let me just uh, generally, I would say yes. If there is a state, I think it tends to be sort of maintained outside of the model, at least a sort of a state beyond like the features. Sorry, not the features, the parameters. I mean, you could say parameters are a kind of state. Um, but yeah, so generally when you have an AI app that is, maintaining state in some way, it's maintaining that state outside of the model and then feeding it back in each time. And, it may even have to be flattened out, for example. So for instance, if you go to use ChatGPT, or I use perplexity.ai for web searches sometimes. I've also used uh, Gemini. In all those cases, there is some state that's being stored, but you'd have to say that that state was being stored outside of the model. Um, but this is also a kind of an area of debate. There is a certain, and I would say the majority of people who are in generative AI, they see the existing models as enough to be able to scale, and eventually get to um, uh, AGI. You also see some, there are some people who tend to say that in order for models themselves to kind of reach a point of AGI, they need to keep some kind of state. And there's the predecessor to machine learning is symbolic AI, and so you sometimes hear people talk about it, hybrid models that do symbolic AI and machine learning working together as maybe a, a paradigm for reaching AGI. So yeah, so I guess I would say like in today's world, the transformer based large language model or generative AI model, it is stateless. Any other questions?
I guess we are good, Peter. I did not see any other question into the chat window.
Sounds good.
Thank you everyone for the joining, and thank you so much, Peter, for great presentation. I request my audience, if you like this session, go to the LinkedIn or the social media where you are and spread your love for our speaker who is helping you with the great content in the free content for you. Thank you everyone for the joining, and thank you, Peter, for such a great session and sharing your knowledge over the weekend.
Thanks, Amit, and thanks everyone.
Thank you everyone. Bye bye.